Just checking the microphone. Good morning, and welcome to Microcontrollers with kingernorth. This is episode 5 of a new series that I started just a few weeks ago. Today we're going to talk about analog in, mapping, pulse width modulation out, using both CircuitPython and Arduino. So let's get started. Let's have a look at what we're going to be using today. So today we've got some familiar items here. This is the things that we've been using these last few sessions, these two main boards. First of all, we have an Arduino Uno. So that's this one here. This is a very popular board, been used for lots and lots of projects over the years. This has been around for quite a while now. And it is very popular because it's relatively easy to use and has some reasonable uses out there and is reasonably easy to use. Secondly, I have this one here, which is called a Feather M4 Express by Adafruit. Now this one I'm currently using CircuitPython to run it, but it will also run on Arduino and it will run quite well on either language, but it's primarily designed to run with CircuitPython. This is a newer version of Python that is an offshoot of MicroPython, and basically it is a simplified user interface to create quick programming and quick debugging. And we're going to see how that works, because that's where we're going to start today. Is we're going to start with the Express M4, or the Feather M4 Express as it's properly called. It actually says that on there, and I'll zoom in. These are the finished boards, what they're going to look like when we're finished building this project. And just to point out a couple of the components on here, we have an LED over here with a resistor. We have a variable resistor here. This is referred to as a pot or a potentiometer. And this one happens to be 10,000 ohms. 10,000 ohms you're going to find is a very common use for input devices for an adjustable pot for any of the microcontroller boards. Pretty much all of them, actually. There's one here on the other board as well. I got a couple of them set up already. I have a bunch of other little items here I want to point out. These are all 10,000 ohm pots as well, or potentiometers. These are just different physical styles. This pot is so popular that it comes in many different styles. This one here uses a small screw on the end to adjust it. This one here has a larger screw spot to adjust it. This one's got a small knob, and these other ones have bigger knobs built into them. So they have many different styles out there for whatever's convenient for you to use. And I just like these bigger ones for when I'm breadboarding things. These also can be mounted in a panel, so they're very easy as a user interface. These other smaller ones are good, This one in particular, this little tiny, tiny, tiny one here, let me put it in my hand to show you how tiny it really is. That's how small it is. Now that little pot, with that little screwdriver end on it, it's got that little brass piece sticking out of it, and it's got a slot in it. It uses just a slotted screwdriver to adjust. This one actually takes many, many, many revolutions to turn. I think this one's about a 20 turn pot. So it takes about 20 turns of resolution in order to go from 0 to 10,000 ohms, which is really handy when you need fine adjustments. So that's what you're going to use when you have a fine adjustment to make. And we'll actually put that in at one point just to show how that works, because it is a little bit different than the rest of them. These other ones all are less than 360 degrees of rotation. And that means that in less than one turn, we go from 0 to 10,000 ohms. So getting to an exact number is not easy with these ones, but it's okay for most practical uses. You can actually find you're going to work out really well. And that's going to take us into one of our topics when we start talking about it and we actually start programming. We'll see how that resolution, I like to call it, how much turn for how much value you have, and how we can manipulate that. That's what today's topic is all about. How do we take an input signal that's of one resolution, and then what we're going to do is we're actually going to, for today, we're going to dim or fade an LED from bright to dim by making an adjustment externally on this pot. And this allows us to take your standard LED, which you normally see at one brightness, and allow it to have almost any brightness within a range that you want to have. And we're going to be able to do that on both of these boards quite easily. They do it a little bit differently, which is expected. We're using two different languages, but they also have different resolution rates. And we're going to look at how that applies from one to the other. So let's get started. And we're going to get going, and I'm going to go to my standard screen here, and we're going to start, like I said, with the Feather M4 Express. So that's what we're going to do. So welcome to whoever joined us, and I'm going to move the Arduino board out of the way. We're going to start by doing that, and we're going to move all these other pots off to the side because we don't need those right now, those potentiometers. And we are going to work on this one here. And the beauty of this is that we can actually zoom in a bit. And I'm probably going to take some wiring apart just to show you how to put it together, because we want to make sure that you understand exactly what's going on here. In fact, actually, I could probably turn that. I want to go that way, or we can actually spin it around. There, we'll make it. We can get in a little bit closer that way, and we can see what's going on this board. So this will probably make it easy for us to work with. So let me go to my standard screen and we'll get started. For programming in CircuitPython, we like to use a program called Mu. Mu is just a preferred language, but any text editor will do when we're talking with CircuitPython. And the joys of this is we're going to make life easy. So I'm going to start by removing the wiring that's on here so I can walk you through step by step of what's going on. I'm just going to take everything off of this. I'm going to leave the pot where it is just because I got it plugged in there already, and it's into 3 spots. In fact, you can see on the back side here, those are the connection points there, each of those silver areas, the 3, 1, 2, and 3. And the center is the movable part that we move with the dial, and the other 2 are fixed endpoints on the 10,000 ohm resistor. It's like a big wire wound resistor inside, and then we run a little contact across those coils to get the variable resistance we need. So that's what we're going to be using for this project. So there it is there. So when I'm starting my programming here, you're going to see that we're up here at the top. We like to start with a comment at the top, so let's give today's topic a little comment right at the top. We start with the hashtag mark in here. In fact, what I'm going to do is I'm just going to zoom in to get you really visible on what's going on. And this is testing a Feather M4 Express, and we're going to go down here and we're going to put in another comment here, so I'll use another hash mark here. or pound sign. It depends on what era you're from, whether you call that a pound sign, a number sign, or a hashtag. So take your pick. It's all meaning a comment in any case. And this is a mapping program. And I'm going to use that word mapping. And what that means is we're going to take a signal in. We're going to get it in a raw value, so it's going to come in a number. And then we're going to put it out as a different range of numbers. So we're going to manipulate it within the software. So we have to import a few different files in here. And there's going to be a couple of things we're going to need in here. We're going to put a delay in at some point. So what we've been finding when we've been programming in CircuitPython, we start with import time. Not if we spell it right. So import time is going to be a big factor of what we do here. The next thing we're going to do is we want to bring in all the pinouts on the board. So we're going to import board. Don't forget that there's basically nothing loaded in by default on CircuitPython, so we have to bring everything in. But that saves us space because we're only loading in the parts that we want. One of the other things we're going to do is we're going to need to do a couple of things here. I'm going to do something called import, and I'm going to call it simple IO. And I'll come back to what that one is. That's actually going to be an add-on file, so I'll show you where to get that from. I'm going to import pulse IO. Now I know I need to do these, so I'm going to go ahead and show you where I get these from. Let's see, anything else that I need to do here? Oh yeah, I need to bring in one more because I'm going to bring in an analog input on that pot. I want to bring in that variable signal. So I'm going to be putting in here from analog, and it's going to be analog IO. And this will be import analog IO. Now I know this seems hard to remember at first when you're first doing this. Oh, good morning, Walter. You made it. Okay. So it's not always easy to remember these, but there are all kinds of help files. There's all kinds of help files for CircuitPython on the Adafruit site. So you can get into more details with this as you build your knowledge in this language. And in fact, actually what we're doing is we're not importing analog IO, we're importing analog, let's get to the proper spot here, in. Because you can import analog in and you can also import analog out, but right now we're just having to use the in file. So a couple of different things we're going to do is we're going to start by actually working on our program. I'm going to zoom this out just a little bit, just because I'm going to run out of room really fast here, and I can scroll, but I'd like not to scroll for a little bit. So those are all our basics here. I talked about simple IO up here. Simple IO is an extra file that we need to add. So we're going to show you where to find that in here. So I'm just going to hop in here and I'm going to jump into something. And I have it here, Explorer, should be right there. And what we're going to do with that is I'm going to go up and I'm going to go to my downloads folder or my documents folder. And in here I've created one called CircuitPython, just to make life easy for you. So within CircuitPython, I'm going to open that up. I have a thing called libraries. These are all those helper files. Now the beauty of this is that you just keep loading them up by date. There's actually a newer file out than this, but we'll be fine with this one today. I'm going to open up that file, and in here we have the library files themselves. We have a README text, and we also have a versions text. And this tells you the version of every file that's inside of that library file. The examples is also where you're going to get a lot of basic information. There are many, many, many examples in here. There's well over 100 examples in here that tell you how to use most of these library features directly. But we're going to go into library. We see that we have all these different file folders. These are groups of information. In fact, there's one on Featherwing if we wanted to add a bunch of things from Featherwing or inside of that. But we want simple IO. And actually, if you scroll way down past all the Adafruit labels, because these are alphabetical order, as you can see, there are a lot. Way down here at the bottom, there's something that comes in here. We had neopixel.mpy, which is just a compressed Python file. And this NeoPixel is the one we used on the very first week. That was the one I used to talk to the NeoPixels when I was just introducing the two languages. Here's our simple I/O. So we would take that, copy that, and the beauty of this is that when I come over here, I'm going to plug in my USB cable for the CircuitPython board now. And as I do, we're going to see that it actually came up here as CircuitPy for Python. So inside of here is a folder. In fact, I can just click on that. There's a folder called library. So I'll double click on that. And then you can see I've put in here simpleio.mpy. I've already added that to that folder. But I would simply drag that out of from my C drive where I stored the libraries, and I would just drag it and I would drop it inside the lib folder within the actual board itself. And this is one of the beauties of talking with CircuitPython, is the fact I can actually see it and work it like a USB device, because it actually is, as far as we go. Adafruit motor, if you remember last week we were playing with servos. This was where the servo file was located within this folder here. So we can just come back out here. We'll see that there's a number of things in here. The ones with the dots are actually hidden files. We don't actually see them. They're there because it creates it in the background. And we have a boot out text, which tells us which version of CircuitPython's been loaded on here. And then we've also got code.py, which is where we're going to be storing all our code when we get to it. So that takes care of all of that. So that we had to add today to the library folder. We had to add that simple IO, the one from our main sheet. So let me just turn that off and we'll get back to our page here. So there's that simple IO. All these others are already part of that CircuitPython file that came into it, part of that bootloader. So we just have to say we want to use those, and it will put them into active memory for us from stored memory, from storage on that drive, on the drive on itself. Don't forget that thing has a lot of memory on it. So we're actually able to utilize that. So from here on, we want to get into our main program now. So we're going to have to write the program. When we do it in Arduino, we use void loop to create a main repeating program. In CircuitPython, we're going to use while true. And this is just the way the programmers have decided to do it. And I'm going to tab in. I ended while true with a colon. You end it with you use a brace, an opening brace, when you're going to work with Arduino. This one you just work with a colon, brings it in, and now says all of this is going to be contained. Anything that's indented here is now part of while true. So we're just going to do something. So first thing we need to do is we need to bring in the value from the pot. That's going to be the first thing that we're going to have to do. So we're going to have to do a couple of things here. We're going to have to define the pot. We're going to have to give it a name. So where we're going to store that is just going to be called pot value. And if I learn how to spell this morning, we'll be just fine. And I'm going to say it's going to equal something. So what we have to do is pot value is going to equal something. And this is just our number that we can manipulate within our program. We did not have to define that in here because this is the first time we're using it. It will define it automatically if you don't include it somewhere else. But in here, we're going to have to define which analog input pin we are going to use. So I'm going to come back up here before the loop. This is part of our standard that we've done in the past. Add comments at the top to tell you what's going on. Import all your helper files. Then define any variables or board definitions that you need. And in this case, we have to do the board definition. So we're going to call this just simply pot in, because it's going to be an input. So I'm going to call it pot in equals, and I'm going to call it analog in. Beauty of this is it starts writing it for me. It knows from the fact that I'm using from analog IO, I have two possibles here. So I'm going to use analog in. So I just make sure it's highlighted. And where is it? Analog, and just hit enter, and it brings it in, and it's called analog in. And now I have to define the pin. So where I'm going to do is I'm going to define the pin as board, which I also imported at the top, and I'm going to tell it to import this on pin A5. And A5 is built into the definitions for this board. In fact, when we look at this board here, these are the analog pins along this side. Let's just zoom in on that so we can see it a little better. There we go. We can see from here we have analog 0 through analog 5. And I just chose 5 because it's closer to this end where I need to hook up the wires. So analog 5 is going to connect to the center pin of this pot because that's the one that's going to be on the moving dial. So that's going to be our variable input. So that's very easy. I'm going to grab a jumper. I'm going to connect it here. That's connected to pin A5. And I'm just going to connect it to the center pin over here. And there it is. It's connected to the center pin of that pot. These little rows across here just go across each side. So the center pin of that pot, I can see that center pin is actually connected to the orange wire. And that orange wire is then connected back here to A5. So that's what we just did. And that's how we told it to do it within our program. We've gone into this program and we've said, hey, attach this value pot in into here. So now I can say pot value equals pot in dot, and the nice thing with the way these are structured, I can just put in the word value and it understands that it's value. Unlike Arduino, it's the end of a line. I don't have to put anything else in here. So what's going to happen is every time it's going to bring in the pot value and it's just going to read it. Now, what I want to do in here is I want to print this to somewhere where I can see what the value is. And we're going to play with that. We want to do it for a couple of reasons. So what I'm going to do is I'm going to add in a quick print statement here. So I'm just going to go print, and I'm just going to put in here, and I'm going to say pot value. I'm going to put that variable that I created in there. So it's going to print that pot value. And one last thing to get this going, we don't want this printing too fast. We've seen in the past is that if we try to print too quickly to the interface, which is called it's the serial monitor for Python, which is actually referred to as REPL, R-E-P-L, what we're going to do is we need to slow it down a little bit because it's way too fast for it. So we're going to put in a time sleep function in here, just like we've been using in the past. So we're going to have time sleep, and we're just going to delay this for 1/10 of a second. 1/10 of a second is 0.1 because in Python, we measure in seconds in the timer. And that's it. That's our whole program. If we've done this right, I should be able to download this to it. And with a couple more connections, which I think I'll go over, we're going to show you what's done. So let me just back this out a little bit. Let's finish our connections. There we go. That'll give us enough room to work. I'm going to take a red wire here, and I want to connect it from the 3 volts. In Python, we tend to use 3 volts and not 5 volts for most things. And I'm going to connect it to the positive rail here. And that's all I've done is I've just brought it out to this long rail beside the red line here with the with the positive symbol at the end. And I'm going to do the same thing for the black wire. I'm going to go to ground, which is 2 pins over. And I'm going to connect it to the brown ground rail, which is the blue lead all the way down this side. Now what I need to do is I need to connect one side of the pot to ground, and I need to connect the other side of the pot to 3 volts. So that's all I've done here, is I've taken the pot and I've connected it across the fixed points. I've connected it between 3 volts and ground. So it's going to have 3 volts across that 10 ohm setting. I'm going to have a center lead coming off of that to tell me how close I am to 0, or in other words ground, and how close I am to full voltage of 3 volts. And I'm going to put that in on pin 5, A5. So let's go ahead and save this now. So I'm going to go up here. This was a new file. It's got a little star beside it, or a little asterisk, and basically that just means I haven't saved it yet. So I'm going to hit save. And you won't be able to see this yet, but basically it's pulling up just a file manager type window. You don't see it because of the way that it displays here on the screen. And I'm going to save it in the root of CPY. In fact, actually, you know what? I'm going to make you see that screen anyways. I'm going to very quickly add a source for that. Let's see here if this will... I don't think this will do it here. No, that one's not going to do it. That's our other screen. So my save as screen, I can add that source in here. Let me go screen capture, window capture, and save file. So there it is there. There's a typical save file screen. So it's going to ask me, where do I want to save it? I want to save it in G. And that's all I want to do, because I want to save it with that name, CodePy. So down here in the name, I'm just going to actually just click on that name just so it uses that name, CodePy. That's our default file name for which gets loaded first. And I'm going to hit save. Now it popped up a little screen that says, do you want to replace this because the name already exists? I'm going to say yes. And I'm going to do that. And when I did that, it went back to the other screen. And in fact, just let me turn off the save screen now. So there it is there. We're back to our regular screen. Now, what I'm going to do is I'm going to turn on the serial monitor, and I just click here. And we can see a bunch of values going by. So I can see a value there of 48,000 and change going by right now, very quickly. So what I'm going to do is I'm going to turn this pot. And you can just see my fingers at the top. I'm going to turn it counterclockwise all the way down towards the ground pin. Now I can get this somewhere close to ground. It's hard to read 0 because these things are all push pin connections. There's always a little bit of resistance there, so we're going to see a little tiny bit left over, and that's pretty common with these things. But I'm going to show you how to program around that. But let's see what the number goes up to when I go all the way up to 3 volts now. So we're going to go along here, and I'm going to keep increasing it clockwise until I get all the way up to the top. And I actually reached a value here of 65,520, which is actually really, really close to the maximum value I can get, but it's not quite maximum of this range of this input. And there's a reason for this. Even though I'm asking for 3 volts, and it's actually closer to 3.3 volts, what happens is that it doesn't work that way. Because our supply, everything has a little bit of variance on it. It's probably sitting at around 3.2995 volts, something really close to 3.2995, with something that's really close to 3.30000 volts. That's very common. So you get something close to maximum. And we also got something close to ground. How did I come up with that number of 65,000 and change? Well, it's actually a math term. And the way this works out, this has got a resolution. Everything has resolutions in here. When we're talking CircuitPython, the analog input actually goes from 0 to 65,535. That is 2 to the power of 16 minus 1. So it's actually it's a signed 16-bit number. And that's the positive value, is 2 to the power of 16. So that's the resolution on the inputs. So I see something close to maximum, I see something close to minimum. In fact, if we went a little over 3.3 volts, we could actually drive a little higher. It's just that we would have trouble seeing it because it's only 16 bits of 16 bits of resolution. So this is how it works. And what we see here is I can adjust this. And I can get values. If I want to go to a value of 30,000, I can try to get close. But because this is such a pot, remember I said this is less than 360 degrees worth of rotation. So trying to get that to adjust, I'm pretty close. I'm bouncing between 29,000 and 30,000, and I'm going on either side of it. So I've actually been able to get close to 30,000, but to get to exactly 30,000 is really, really tough. And that's just the reality of these pots. But it's close enough for probably anything we're going to do. So now that we have a value coming in, though, we want to do something with it. Well, the one thing we can do with all of these things is we can actually light up an LED. And an LED, we want to be able to make it fade. And this is how it's going to work. We're actually going to take that input signal, and then we have to change it, convert it to something that the output can recognize. So what we have to do is we use a device, and we use a pulsing method that we refer to as pulse width modulation. Now, you may or may not be familiar with pulse width modulation. A lot of people are not, and that's fine. So what we have here is I've called up this little chart. This little chart will give us an idea what pulse width modulation is. And we actually used it last week on our servos. Last week on our servos, we had to set a frequency of 50 hertz. This time, we're not going to set the frequency. We're going to let it go as fast as it wants. I think the default is around 500. It will actually go into the thousands and higher into the cycle rate. And that is cycles per second. So how many time intervals per second is frequency? And cycles per minute, actually cycles per second. So in here, we can look at it. If something is considered to be a 100% duty cycle, in other words, it's always on. And that's pretty straightforward for these things. This is going to be always on. When we go up into an 80% duty cycle, what that's telling me is 80% of the time the output is on. For 20% of the time, the output is off. And in the next one going up, it says 40% duty cycle. That one there shows it in blue as the on cycle, which is about 40% of that time period. And about 60% of that is going to be off. And the top would be 20 and 20% on, 80% off. And of course, the 0% duty cycle would be always off. And this is how we create little pulses. LEDs are not good with varying the voltage. They like a nice voltage of about 1.5 volts across the actual element, providing we put something in to limit the current, because you need about 3 volts minimum to light up an LED. Actually, it's about 2.25, 2.5, depending on the LED. But we need more than 1.5 volts. Now, across the LED itself, we only drop a small portion of that voltage, of that supply voltage. And what we need to do is we need to pulse it to make it look like it's fading. So that's what we're going to do. So let's try and make that happen. So in my program here, I'm going to go up here and I'm going to turn off the serial monitor for now, because we're going to have to expand this program a little bit. So what I want to do is I want to know, and I'd have to take this value now, and I'm going to write it out to the value here. So what I'm going to do is I have to be very careful about what I do, because there's a limitation on the range of resolution for the output. And unfortunately, as it is on virtually every microcontroller, the range coming in is not the same as the range going out. I didn't create it, it's just the way it is. So what happens here is we have a range from 0 to 65,000 roughly on our input. We only have a range of 0 to 32,767 on this particular board, which is still much finer than when we go over and I'll review the code that's in the Arduino. This has a bigger high range, but this is 2 to the power of 15 instead of 2 to the power of 16, so it's 1 less bit. It's half the range. So what we're going to have to do is we're going to have to do some manipulating to it. I'm going to start by just turning this down. I'm just going to go there and I want to turn that down to a really low value to make sure it's really low. So I can show you just the simple thing here if we only want to use half the pot to make an adjustment. So what we're going to have to do here is we're going to have to, first of all, we're going to have to add some code in here, but we're going to have to connect a pin to it to do our pulse width modulation on. So I'm going to go ahead and do that first. I'm going to go to pulse width modulation, that's just the name of it I'm going to give it, equals, and here's where we use pulse IO, which is built into the board, dot pulse width modulation out, and then we're going to pick a spot on the board to connect this to. So I'm going to have to go board again, and I have to pick a pin. Now luckily what happens here is that we have a couple things we can set, and this pops up in a pop-up window that you can't see because I'm typing, but you can actually set a few things in here. The first variable we're going to set is the board pin. So we're going to set this, and I'm going to set it to D13. And then what you could do is you could add a comma, and this is where you could put in a fixed duty cycle to start with. A duty cycle of 0 would be off all the time. A duty cycle of 2 to the power of 15, or just putting in 32, actually 2 to the power of 15, or 32,767 would actually be 100% on. So that would be duty cycle equals the full value. And then we've got the frequency, which is default is set for 500 hertz. And then we have a variable frequency. Can we change it or not? The default is that it's set to false, which means it's going to stay at 500 hertz and just stay there. But we could change the rate that it comes out at, and you can set that to true if you need to vary it. And you do those when you're getting into sound. But because we're dealing with light, 500 hertz is a really nice speed. If you get down to that 50 hertz that we did with the servo last week, and you get down a little bit lower, and you get down to 20 hertz, you can actually start seeing it with your eye. You can actually start noticing a flicker. And we want to eliminate as much of that as we can. So right now, for this time, we're only going to set up just the pin. That's the only thing we need to set up for this lab today, for this experiment. We don't need to go into all the other settings. If you want to find out more of them, there's lots more information out there available on that. And maybe at some time we'll go into pulse width modulation in a lot of detail and play around with it. When I start doing things with sound, we're going to manipulate more of this. But for now, we're going to leave it here. So now let's put in something here to set our output. So what I'm going to do here is I'm going to choose pulse width modulation, which is my variable for that pin. And I'm going to say, what's that going to equal? Well, actually, before I say what it's going to equal, the thing I want to adjust is the duty cycle. That's how much I showed in that picture, how much the on time is compared to the off time. So what we're going to go in here is we're going to type in duty, I got to put a period in there, and then duty underscore cycle, and you can see it's already trying to fill it in, or you can't see it, but it does. It starts to fill it in on our page. And we're going to go duty cycle. So that's great. So it's filling that part in for us. And then what I'm going to say is that's going to be equal to, for now, I'm going to say pot value. But I'm not going to leave it there, because we know the pot value can go higher than the duty cycle can. So because the resolution is different. So there's our very simple start to this whole thing. So I've created a nice little simple program. I'm just going to bring this pot value in. The one thing I have to remember is my duty cycle is half of what that pot value can be. So what I'm going to do is I'm just going to open up my serial monitor so we can see that number in there. We're below 32,000, so we'll be good. I'm going to hit save. Oops. Pulse IO. I spelled Pulse IO wrong. Look at that. See how this error works for me? I like this. And it's because I went down here and I can't spell. There we go, Pulse IO. Now it's happy, it's got an E in there. If I hit save again, it should be fine. And there it is running. Now I want to point out something that happened here on our board. And I'm going to have to create a little bit of a shadow here. Right here, we've got a little red LED on in this top left corner. Okay, so we can see that. As I bring this down, we're going to see that LED, that red LED is fading away. And it almost shuts off when I go down to 0, but not quite, because our number isn't quite at 0 on the screen. In our REPL, we can see that it's slightly above, so it's still sending a very small amount out here. When I turn it up, I'm going to increase that until I get close to 32,000. And we're going to see it's quite bright. So I'm actually able to dim that light on there. Now this is an advantage on this board compared to many others. This is on pin 13. The advantage with most CircuitPython boards, especially these ones that are made by Adafruit, those pins all have the ability to use pulse width modulation. That's not the case when I get to an Arduino. Arduino has specified pins, and I'll go over that very quickly when we get to that part of it. So I can get there and I can go up to pretty much full brightness. I really don't want to go over because it may not be happy. And I'm actually just slightly over, but we're at 100% output. We can see that red light is nice and bright. And that's what we want up there, is that light is very, very bright. I'm going to bring that back down a little bit. But we need to do something better for this, because what happens is we can go too far and make it overly bright or beyond the capabilities of the pin. and yet we can also go so dim that it doesn't quite shut off. So let's fix that in our program. And this is where mapping comes into it. So we had analog in, and we've got pulse width modulation out. Now what we need to do is we need to create something called mapping. And we do that down here in the program. So I'm just going to turn off that serial monitor to give me more space to write here, code here. And we're going to put this in. And where I want to put it is between these two values right here, the mapping. So what I need to do is I need to put a new line in there, and I'm going to create a mapping instruction. And when I do this, I'm going to create a new variable called map value. You notice I don't have to define that anywhere, except we'll spell map as map. Map value, and this is going to equal something called, and what I'm going to do is I'm going to put in here something called math dot truncate. This is actually a special math instruction, so we're going to have to do one more thing. I'm going to stop there for a moment, and I'm going to come back, because up here, I didn't import math. So somewhere up here, I can do this after the board. I'm going to do an import math. These are more than just basic instructions. Math truncate is a very special instruction. Let me go back down to this instruction here. Math truncate, what that does, it gets rid of all the decimal places. Because we're not dealing with decimals here, when I create a mapping value, I don't want decimals going out to it. These like integers. These numbers, this pulse width modulation duty cycle likes to be an integer. The number coming in from the pot in dot value is also an integer, meaning there's no decimal places. So when we do our math, we want to make sure that we truncate it to get rid of any decimal places that are created. So I'm going to go in here and I'm going to use now my simple IO instruction. I'm going to say dot, and this is a special feature they have in here called map range. And what that does is it lets me specify some ranges to my math. And I'm going to actually, I'm going to leave that size, and we're just going to have to scroll the screen around a little bit to see what I'm typing in here. So I'm going to start by telling it what my input is going to be into math range. And that's going to come from pot value. That's where we're getting our supply number for this math instruction. And then I'm going to put in a comma, and I'm going to give it a minimum range. Now we know we get a few numbers in there, so I'm going to say 500 is going to be my minimum input, because I don't want to go to 0 because I can't dial down to 0. So this is the numbers I get from the pot itself. So my minimum value I'm going to set to around 500. My maximum value, I know I can get to 65, whatever it was, 65,520. So I'm going to say stop me a little bit before that. I'm going to stop around 64,000. Probably be close enough. And what I want to do is I want to map that out to a range that works for pulse width modulation. 0 is the minimum value. And I told you that the other one was 2 to the power of 15 minus 1. It's going to be 32,767 is considered 100% or 100% duty cycle. And I'll just put a bracket behind that. So now we can see this is actually our math problem here. This is the big range that we're using up here. So this range, just to go over that again, we're using simple IO, which we imported. We're going to use a function within there called map range. We start with the value we want to start with, which is called pot value. We're going to say, hey, take the pot value of 500 to 64,000 and rescale it or map it from 0 to 32,767. Now, there is a math formula for this. If you multiply the top against the bottom on the opposite side, and you do all of that, and you divide it, and then you multiply it by the pot value, and you go through and everything, and you'll get the answer to the new scaled value. Well, rather than having to figure out and making sure that our math is right every time, we just use a function that somebody's actually done that for us. So now let's get back to the beginning of this line. Oops. This is always fun. There we go. So we see that's done in there, but that's called map values. So now duty cycle is not going to be set to pot value, but to the mapped value. So there's map value. So now we're going to do it that way. I'm going to open up that serial monitor. I'm going to tell it to save. We're going to see, oh, it doesn't like something. Invalid syntax. What did it like? Oh, import math. Let's see if I did this right. Did I miss something in here? Simple I/O, map range, pot value. Oh, silly mistake. Something to watch for when you're programming. If we follow across this line here, I have an open bracket and open bracket. Watch when I get to the end of this. I only have one closed bracket. I need a second one. Simple mistakes. It told me the error was on line 17 because it didn't understand what was line 17. It's because I hadn't finished line 16 properly. That's like forgetting to put the semicolon in when you're doing programming in Arduino. Easy to do, and we all make mistakes. So there we go, and we're back to here. So now if I save it, it should be fine. And we can see that value has dropped to 14,000. So now let me take this, dial it down towards 0. I can see I'm not quite at 0. And yet my LED has turned off up there in the corner. Top left corner of the screen. Now I'm going to bring this up. You can see there's that LED starting to glow. It's increasing. And we can take this pot now and go all the way past the middle, which takes us up to the high value, and we can see what's happening there. So that's what we get now on our item. We're going to make one more addition to make this clearer for you before we go on to the Arduino version and show you how it works. Okay, so I'm just going to turn off the serial monitor because this print value is only showing me one value. We're going to create a better print statement here. So what I'm going to do is I'm just going to simply go in here and I'm going to edit this print statement. I'm going to go in and I'm going to add the word raw, colon, and I'm going to put in another double quote, comma, and I'm going to put in pot value. So now it's going to put the word raw in front of the pot value when I'm printing out that line. And then I'm going to put in here and I'm going to go mapped. And I better put that inside of quotes, mapped, colon, mapped, and there, comma, and I'm going to go map value. Okay, so now what I've done in this printout statement here, I've started with the word raw. This has actually gone to a slightly different color. It might be hard to see on your screen, but it is a slightly different color, the word raw and the word map, because they're inside quotes. It's going to put in the value, and then it's going to put in the other value, and we should be able to see it all. I'm going to go back to my serial. There's what it looks like now. Let's save it. Now we actually get text to go with it on our REPL, which is really nice. So you can see now that the mapped value starts out at 65,540. Let's just scroll in our program there. When we did this value over here on this side, if you remember, we went 64,000. So I should be able to start turning this down. And it's still showing at 32,767, but as soon as I drop below that 64,000, that number starts to change. And of course, so does the brightness of my LED starts to come down. We can see that those two numbers are moving together and it's remapping it. And you can see when I get down something low here, I get below a certain threshold in my there, and I said it was 500 or something like that. Everything below 500 counted as 0. So now I have a definite off with my LED. If you remember the first time I did this, I had that little tiny flicker of red that was showing up in there. Now it's completely gone. Good morning. Good morning, Brian. Nice to see you join us. Okay, now Brian and Walter, you can say hi to each other. You're both on there. Anyways, and they know each other as well. Just for everybody else. So you can actually see what's going on here. So we've done all this mapping, and it actually works out pretty good. It gives us a nice resolution, allows us to fine-tune it, and we get lots of control. Like I said, in CircuitPython, I could take that LED and I could connect it to any one of these digital pins now, and I could also get the analog out on those, because all of those pins are pulse width modulation available to us. You just have to use it and set it up like I did on rung 12 in the program, where it says pulse width modulation equals pulse IO, pulse width modulation out, and then set the pin number you want to connect it to. So it's actually very versatile. I use the onboard LED because it works with CircuitPython. It does not work the same way in Arduino, and we're going to go over that in a moment. I do want to show you one other feature. And remember I talked about this other types of pots? I talked about these at the beginning. I had this little tiny pot here. This is a precision pot. This is lots and lots of turns to equal 10,000 ohms. So I'm going to unplug this one, and I can do this while it's running. I'm going to plug this one in here. I'm going to make sure the center pin line, actually, I'm going to probably turn it around this way. Not that it makes really any difference. And I'm going to have to move these other pins over because they're all side by side. But we can now see in our program we're at 51,300 and something. It's actually a little bit steadier. Now what happens here, I'm going to try and turn this without increasing it, and it's actually taking me a lot of turns to get that to go up a little bit. And pardon my finger there. Actually, I will take this. I'll turn it around, which is going to reverse everything. It's now down at the low end. But what I'm going to do is I'm going to actually hold that, and I can turn it multiple times. And we do get a little bit of a drop in the numbers. So I can actually dial that down. So as I approach, and is that bringing it up or down? Let's see here. That's actually taking it up. That's because I've reversed the wires to connect it. But the nice thing with this, I wouldn't want to do this if I had to make a lot of adjustments to it. But to fine tune it once is great with something like this. And then you only use them when you need to. But it's very, very precise. I wanted to see that 500. Oh, there it is there. I can go. I'm seeing just over 500, a little more. And as you can see, I'm seeing a number coming out every once in a while, bouncing inside the file. Because still, these are not soldered connections or anything. So it's just kind of there. It would be better if I hard fixed these. But you can get quite the resolution, so I can see it there. A very small number, and I have a very, very tiny bit of red light up here, way up here in the corner on this board. So it does work, but that's how it works with one of those precision pots, is you can get a lot of fine adjustment. So easy to work with. So that's how the precision pot can be done. If you need to set something once and you want to leave it there, it can get you a very fine adjustment that you cannot do with the big knobs in the front, the big pots, because they only turn less than 1 revolution for the whole range. This is about 20 revolutions, I believe, this particular pot, to go from 0 to 10,000 ohms, much higher resolution. Okay, so that takes care of that part of it. We're going to look at the Arduino equivalent of this code. And we're going to see some differences. Some of it is definitely easier, but there's limitations within the Arduino, and we're going to do the same thing. So let me just get this other stuff out of the way. I'm going to take that board and move it out of the way, and I'm going to bring this board in, and I better zoom that out a little bit because this one's physically bigger. So there shows me everything I need to see on this board, and we'll talk about what's on this board here in a moment. So I'm going to go ahead and just turn off my CircuitPython code, and I'm going to turn on my Arduino code, and you're going to see that I have the Arduino code fully set in already. So let's go over and have a look at the picture, and let's see how this is connected before we get too far. So I'm going to go in here to my big picture of my camera. So here we go. So the Arduino comes in here. It's hooked up. Again, I've taken the positive 5 volts in this case, because this is 5 volts in Arduino. and the ground, and I've connected them to the outside rails over here on this side. And you can see in here, tightly in here in the middle, because that's where they roughly lined up, the red and the black are connected to the two rails. Red is the positive rail. The black, or sometimes blue, in this case it's black, is the ground rail or common. What I've also done is I've taken the middle pin from the pot, which is the yellow wire, and I've connected it over here to A0. Now you can use A0 to A5 just like you did in the other one. I tend to try not to use A4 and A5 because they're dual purposed, but and in CircuitPython I do it the other way. I try not to use 0 and 1 because they're double purpose, because they can do true analog out, whereas these are all analog in. These last two are done for special communications we haven't talked about yet, and we will in a future show. The second thing that we are doing here is we are bringing in our LED. There is an LED on board on this, but we're not going to use it. In fact, it's right there where I'm pointing. In fact, let's move the yellow wire out of the way. It's marked with an L on the board, and that is the pin, that's D13 on that. A lot of places use pin D13 for an onboard LED. Even though they don't have to call it D13, they do because people are used to programming it. This is not a pulse width modulation output. It's strictly an on or an off output. So that's a problem. With Arduino, you'll notice that down this side here, there's these little symbols, and that's actually a tilde, that's that little squiggly line. And that tilde tells us that this is usable for pulse width modulation. Now, on this particular board on the Uno, and it will vary from board to board, but an Uno uses pins 3, 5, 6, 9, 10, and 11 as possible pulse width modulation outputs. The rest of the pins cannot be used for that. So it can't use as many varying pins. So I brought it out on pin 11 because pin 11 is a pulse width modulation pin. I've run it through a resistor and I've hooked it up to an LED. Same idea as what we had on board. It's just here it has to be mounted in the breadboard. So that's what we have going there. So I'm going to go ahead and power up that board, as it's not powered up right now. And when we do, we can see that it's there. And we now have some flickering lights. We have some different lights that have come on and some flickering that's going on, so we know our board's alive. So that's good. So we now have a board alive. Now, I've already done the easy part. I've loaded in this software here that I've created. And now that I'm on this page, and if I go here, I'm going to bring that up a little bit in size so that we can see it. So again, this one's fully commented. The other program, because I was building it, I didn't fully comment it. I would suggest that you go back and fully comment your program in back inside of CircuitPython. I like to do it all the time when I'm doing them, and you just want to make sure they're always done in there. In here, I've added in the top part here, I've added in notes about what I'm doing, so I'm testing mapping, and I'm using the analog inputs have a resolution. This time it's a resolution of only 0 to 10 or 1023. In CircuitPython, we could go from 0 to 65,535. So this is a much smaller resolution. The pulse width modulation also only goes from 0 to 255 out, as opposed to 0 to 32,767. So smaller resolution. This only has 256 steps, as opposed to over 32,000 when you're talking CircuitPython. And there's no helper files because everything is already built in and everything preloads. We had to add and install all of the pieces that we wanted to use so it didn't take up extra memory in the CircuitPython world. Now, variables, we have to define our variables that we're going to use, and these are all going to be integers. We don't want any decimal places on any of these. So I've basically got my raw in, which is my value from the 10,000 ohm pot. I have pulse width modulation out. That's going to be the value going to the LED. And then we have an LED pin, which is going to be attached to pin 11. So in here, I turn on my serial monitor, which is the function that's used similar to the serial REPL screen in CircuitPython. except here I have to tell it to turn on. So I'm turning on serial monitor, which is a built-in function, and we'll use that. We're going to have to set pulse width modulation compatible pin. So here we're going to use pin mode.led pin and output. We're going to set it as an output because that pin can double as an input as well. But that's all we have to do with it. In our program, basically these are all commented. These are the same types of comments I would put in the finished CircuitPython, and I will show you what a commented version looks like shortly. So in here, I would go in here and I would convert raw input. First of all, I do a read it in. So what I do is I go raw in equals analog read. I'm not doing a digital read. I want to get that variable number coming in. So I want to do an analog read, and it's connected to pin A0. I'm going to convert that to a mapped output. Well, pulse width modulation out is going to equal, and they have a nice smaller version of the map, but it actually works identical to the one in CircuitPython. Just takes less words to write it in front. This one's called map. There's our raw in, so that's our source that we're going to use. 0 to 1023 is the input range. That's the resolution of the input pin, in other words, the analog input. 0 to 255 out, which is the resolution of the pulse width modulation output. So it's the exact same in between the brackets here. It's exactly the same as what it was in CircuitPython, except you match the resolutions to match the board you're using. The analog write is nothing more than me telling what the duty cycle is going to equal to. So I use analog write. I set the pin. I have to remind it what pin I'm going to analog write to. And I'm going to set it to pulse width modulation out. So there's that would be the duty cycle when I'm doing it on CircuitPython. We just simply call it pulse width modulation out. For the printing, if you noticed I did print in one line when I was talking CircuitPython, I'm going to do it here. I'm going to say raw, and then I'm going to go raw in, I'm going to go mapped, and then the final print statement is going to have the line return at the end of it, and that's going to be pulse width modulation out to come down to the next line. And again, I've set 1/10 of a second delay. Delay in Arduino is in milliseconds, whereas as opposed to seconds when you're talking CircuitPython. So just things to remember. It's always great to have. So what I'm going to do is I'm going to open up this. Actually, I'm going to set up my tools here because I have to communicate with it. In here, I'm fortunate I'm already set up for Arduino Uno. You can't see all of this because of the way it captures pages. But I'm set up for the board, which is the Arduino Uno, and make sure you connect to your COM port that is available, and this is COM port 10 that I happen to be using on this one. I'm going to go ahead and I'm going to upload my sketch, and we're going to see on the board, we're going to see the two little lights in the middle here called transmit and receive. That's these two up here. We're going to see these two little LEDs. We're going to see those flicker while it's uploading. So we're going to go ahead and upload. It's compiling the sketch, and then it's going to do the upload, and it won't take very long to actually upload. It takes longer to compile. I don't know why. Oh, there it is. It's uploading. We had the little flickers really quick, and we're all done. Now I'm going to open up the serial monitor, and I'm actually going to add that page to it so you can see. I'm going to show you what the information is in there. So I'm going to go in here to my window. And it doesn't seem to come up as a separate page in this one for whatever reason. It's what happens. So I'm just going to bring it across here. And I'm going to turn on that page appropriately in my code as soon as I can find it. Region, there it is. Well, that's that region up there. I don't want that one. I think it's down here. Here, there it is. And let me turn off a couple of the other things because they're all getting in the way of each other now. And in fact, the CircuitPython one's in behind that. Let me turn that off too. Whoops. Yeah, it doesn't matter. Oh, I know why there's more than one thing showing. But here's our output values coming from the pot. Just to show you right now, that LED is on extremely dim. You can see that. I'm going to cover up there. I'm not going to worry about the board, but I'm going to turn that up. And you can see it brightened up quite a bit. And it gets so bright, you actually can't see it in this. I have to shadow out a lot in order to show you that that's even red in color. But we can see we've taken the 1023 raw value and mapped it out to 255. We're going to start bringing that down. And as we do, that light gets dimmer and dimmer and dimmer until it's just a flicker. You can see that small flicker in the red there. Whoops, until I turn right down to 0 and it shuts off. So I do have range, except I have to use an external output LED. If I tried to do this with the LED that's built into the board on pin D13 on the Arduino, it'll either be on or off. It doesn't go the other way because it doesn't have pulse width modulation capability. It either goes by true or false. So that's just something you have to watch when you're going to the Arduino. So really, that takes us through the Arduino program. That shows you a little bit of difference. So when we're doing that and we're writing in Arduino, it looks like this. It looks a little bit simpler. It's definitely a little bit shorter, but it doesn't have as much flexibility to it, and that's just the reality of Arduino. Arduino's been around a little bit longer. The ranges are a little bit smaller. They're an older board. They just don't have the same capabilities of the newer chips. And Arduino is designing ones that use chips similar to what's in the CircuitPython, and these values would then change according to the new chips. So you just have to be able to keep that in mind whenever you're doing it. So that's what we're going to do. So that's actually how that works. Now, I did want to show you one last little piece, and I wanted to show you a fully commented version of the CircuitPython code. So I'm going to do that. I'm going to go back to this screen, and what I'm going to do is I'm going to move this one out. Gotta love this when that happens. Okay, we're okay there. And we can see I've got my notepad open here, which notepad is exactly that. It's just a text editor. So in here, I've got in here the full comments at the top, a test of Feather M4 expressed by kingernorth. This will be a mapping program. I've used the triple single quote start and finish. This allows me to do multiple lines of comments. When we do it in Arduino, it's done a little bit differently. Let me show you the Arduino screen at the top. I've actually used the /* and / to end it, and that is multiple lines of code or comments in there as well that doesn't get seen by the program. It's hidden from the program. That's what these single quotes do in the other one. So I can have single line quotes here with the hash mark, and then the multiple lines with the triple single quotes. I import all the related boards, and I put in import related files. And that's what I'm doing. Then I come down here for the fully documented version. It says define any variables needed. And I did. I defined pod in and pulse width modulation, which were my 2 pin allocations, where on the board I was going to use them. So that's like my setup file within the Arduino. And then here was the actual program. Again, not very long, fairly short. But the biggest thing in here is read the raw input from the pot, convert the raw input into a mapped output value, which I did through this long instruction here, their version of map range. And then I wrote the map value to the LED, which is just using duty cycle instead of just taking it to be analog write. And then I used the print, which is a single line instead of multiple lines. And it said print the values in the REPL. That's the serial monitor portion. And set the delay to limit the sample rate. And I set it to a tenth of a second. So that's it. So that's how you create the code in both Arduino and in CircuitPython to do exactly the same thing. And I say exactly, even though the resolution is different, they both allow the LED to be faded in and out. And we can manipulate that any way we want now in our program. We could do it automatically. We could have it do it on a cycle. Think of yourself of a thing like a lighthouse. A lighthouse, you see a light come up and it goes from dim to bright quickly, and then it fades back down. And then it goes up brightly, and then it fades back down. You can set a ramping rate for those using for loops and things like that, like we've used in some of the other programs that we've done in the previous weeks. And you can now start creating this fading and bring the lights brighter, hold it on for a moment, and then dim it down. And get a different effect from it. You could take a long time to brighten things up. You can take a long time to dim them down. Or you can do it very abruptly. It's up to you what you want to do. It's your imagination and how you want to utilize this function. But this is how you get a variable input to a variable output and rescale it, or map it, as both of them like to call it, mapping, to an appropriate range so that you don't go past the limits. All right, well, thank you very much for watching. I hope you've enjoyed this. I hope you have learned a little bit something today, and that you've seen it used in 2 different languages, which is always nice. So I'm going to say goodbye, and we're going to say thank you for coming. I'm going to say thank you for coming by. This was Microcontrollers with kingernorth, episode 5. Today we looked at analog in, mapping, and pulse width modulation using both CircuitPython and Arduino. So thank you. You can watch for feeds from my Twitter handle. Go to Twitter and follow at kingernorth, or come in here to YouTube on youtube.com/kingernorth and come and check out my other videos, and please subscribe so that you can keep in touch. Whenever I upload a new video, you'll get notice of it, and you'll be able to tell that it's there. All right, thank you very much, and have yourself a great day.